Yeah.
Oh yeah, after I got some chocolates.
All right, let's get started with our experiment for today. So we've been talking in class a lot about electric dipoles. And in a sense, a capacitor is nothing but an electric dipole, in that what you have is you have a positive charge and a negative charge separated by some distance. So here we have a picture of a positive charge and a negative charge separated by some distance. You can see that there's an electric field between the two. Now notice that since these two charges, they don't necessarily need to be point charges. They could be conducting surfaces. And exactly what those field lines look like in between are going to be dependent on the geometry of the problem, right? For example, if I smushed one of those blobs into a plate, and that one into a plate as well, we'd get those different shapes. Or if one of them was a plate and one of them was a dot, or both of them were plates, we'd get something like what we've seen before, how the electric field lines kind of bend, right? And we know that on a conducting surface, you can see that the field is always normal to that surface or perpendicular to the surface itself. So where does this idea of capacitance actually come in here? Well, capacitance is what we're going to measure in the experiment this week. So Q, the amount of charge on one of the conductors, is equal to C delta V. C we call the capacitance, and delta V is the electric potential difference between those two plates. So in this picture right here, the plus Q has a larger V because you're closer to positive charge. The negative Q has smaller V, or you're more uphill electrically in electrical elevation, and you're more downhill in electrical elevation here. All right, so this is what a capacitor is. So let me just show you a couple pictures here on the screen. Now here's a parallel plate capacitor, and that's the one that we're actually going to be working with today. A parallel plate capacitor is where those two conductors have just been squashed into plates. Now we're not really going to be considering too much the fringe effect, the fringe field. It doesn't really matter for the purposes of what we're doing. Right, but you can see that the amount, what the C value measures is the ability of a capacitor to store charge. So if you have a really large C, you can have a lot of charge Q on your capacitor. That's the idea. Now this C value right here is geometry dependent. It depends on the shape of the capacitor. It depends on how far those capacitors are apart from each other. Now for a parallel plate, the capacitance for a parallel plate, C, is epsilon naught A over D, where A is the area of one of the plates, and then D is the distance between the two plates. Right, but we can imagine, and we kind of saw how we would do that. In fact, just by the relationship between E and V, that's exactly how we find it, and then we just identify the factor that multiplies delta V. We just call that C. Basically, that's how you would actually get that expression right there, and we essentially did that last class. All right, but imagine you could have different shapes. Now typically in a circuit, we're going to indicate a capacitor just by like this, even though a real capacitor in a real electronic circuit doesn't look like that, because the plates, it would be kind of inconvenient to build all capacitors like that because that takes up a lot of space. So what you might do in practice is you might put a little bit of material in between here called the dielectric and then roll it up like a pancake. And then you could basically compress it to a small space. Okay, now you might see a picture that looks like this, where one of the lines is kind of curved. And in fact, on the multimeters, it measures multiple electric quantities, including capacitance. There is a polarized capacitor right here. So I turn that all the way there. and that's going to allow me to measure the capacitance. One of them goes in the common black port, the other one goes in the red port on the right. So these are symbols for capacitors, but of course they don't all have to be parallel plate capacitors. There's other geometries that we could consider. So here's a parallel plate. Now, if I was to look at a cylindrical capacitor, well, a cylindrical capacitor would simply look something like this, where, and in fact, we have examples of those over on the side, where one of your electrodes is actually in the center, and then the other electrode's on the outside. So one electrode's actually wrapped around the other. And in this case, the capacitance is not epsilon naught A over D, and if I talk about a cylinder, we can talk about the capacitance per unit length. 2 pi epsilon naught divided by the logarithm of B over A. You can see B is the outer radius, A is the inner radius. It depends on the geometry. This formula is not so important, but it's just to point out that the capacitance depends on the geometry of the conductors, their shape. Right? So now, what's another possible shape? So cylinders. Another one is sphere, for example, right? Now we could also think of a sphere. You could have one electrode at the center, and then another shell kind of around it. And in fact, you could make the outer shell go all the way to infinity. So here's a picture on the right of the screen, which would be an example of a spherical capacitor. Now you might ask yourself, under what considerations would you design different shapes for different capacitors? Okay. So, but anyways, here's what it works out to be. C equals 4 pi epsilon naught AB over B minus A. So you can see each of these three equations looks very different. It just depends on the geometry that we're looking at. All right, now let's look at capacitors in circuits themselves. So here is a capacitor in a circuit, and this would be what kind of capacitor? Parallel plate. Now, here is a battery, and a battery's job is to act like a charge pump. It creates an electrical pressure and means positive charges want to fall to lower pressure, negative charges want to move to higher electrical pressure. And by electrical pressure, I just mean electric potential, or volts. So what the battery does is it creates that pressure and then thereby charges the plates. So if I add some voltage, let's say I turn this battery to 1 point, as I start to increase the voltage of this battery, and by voltage I mean the top side is 1.5 volts higher than the bottom side, so this would be plus 1.5 volts and this would be 0. The difference is what's important. Because again, your 0 point is kind of arbitrary. You can call 0 anywhere. So as I increase the potential on the battery, you can see more and more charge is pulled off of the top plate. So more and more negative charge is pulled off of the top plate and deposited onto the negative plate. That's how they actually have equal amounts of charge. So they have to have equal amounts of charge because the battery is just like a pump. Now we can think about some things that would happen if I was, and on the top here you can look at some of these meters here, which would, and then you can compare that to the formula right here. What would happen as I increase the distance between the two plates? What happens to the capacitance? Decreases. Now what would happen to the capacitance if I increase the area of the plate? So let's look at the screen. We have a capacitance getting larger And that makes sense. If you have a bigger plate, you should have a larger ability to store charge with a bigger plate, more surface area for that charge to distribute itself over. So what we're going to do is build our capacitor by using metal plates like this, which basically will stack like this. And what we can do is we can vary the distance, kind of like this. It's going to be very important here to measure the distance very, very precisely. And I'll explain in a moment how you're going to do that. But I can't exactly stretch these plates, so you're going to grab medium-sized plates as well, medium plates, and then large plates. All right, so you can change the area that way, and then you can change D. So what you're going to get is you're going to get a graph of capacitance, and you're going to plot A over D. And grab a bunch of data points. What should the slope of this graph equal? Epsilon naught. Epsilon naught should be the slope. Epsilon naught being the permittivity of free space. Well, technically, if we just did the plates like this and there was nothing in between the plates, we'd be measuring the permittivity of air. Epsilon naught is it's called the permittivity of free space or the vacuum. And I'll talk more about that in a moment, how we're actually going to do that, because again, it would change it if you just tried to hold it, for example, or if it was a little bit askew, right, you wouldn't have a perfectly parallel plate capacitor. All right, now let's look at how we're actually going to do this here. Is how we're going to actually maintain the separation distance between the plates. It's by using a physics textbook. So what we're going to do is, I have a bunch of extra textbooks at the back of the classroom. You're going to take a textbook. Right? If you have a textbook that you have, you can use that one as well. Now, different textbooks, the paper composition is slightly different. And also, some are gloss, some are matte, more, and some of them have different ink that they use. So ink is conductive, so there's going to be different properties of the paper. Now the paper we'll call a dielectric, meaning it's an electric insulator. It's not really a good conductor. So if I put the paper in between the two plates, if I put one of the plates in between or in the book, I can basically choose any distance I'd like, and I can build my capacitor kind of like this. This is the sandwich here. Now it's important this book is actually a little bit small. It's hard to fully insert the plate without having a little bit of the edge coming out. So try to find a book where you can fully get the plate inside. It might be hard for the big plates, but if you just have a little sliver out, that should be fine. It shouldn't really make much of a difference. Okay, and then by looking at the page numbers, you can determine a line density, and that line density will allow you to basically very accurately measure the distance between the two plates while keeping them perfectly parallel. Another thing to keep in mind is you want to put pressure on the book. So when it's really thin versus when it's really thick, there's not any air in between the pages. I mean, you don't have to stand on it, but you should just put a bit of pressure on it so it kind of evenly disperses that there. So it's sort of uniform. All right, so that's how you build a capacitor, and then you can use different size plates. You're going to connect the snap connectors on the plates to the multimeter in capacitance mode. It's going to give you a reading here, and notice it's going to say the units at the bottom. So this one says NF, which is nanofarads. So the units for capacitance are farad. So 1 farad, or 1F, is equal to 1 coulomb per volt. All right. The larger the capacitance, the larger the ability that device has to store charge. All right, so one final point about dielectrics, because the purpose of this lab is going to be to measure what's called the permittivity of the paper. So the permittivity of free space, this number right here, we already know is 8.85. What are the units? Anyone remember what the units are for the dielectric the permittivity of free space? Well, if we look at this, this is essentially, it really describes, now, well, let me get back to this in a moment here, but let's say I take a piece of paper and I put it inside the book. I'm moving. If I put it inside the book, what I get is a different capacitance. If I put a dielectric inside, a different capacitance C, which is equal to kappa C naught, where C naught is just the capacitance without the dielectric inserted. Now, what does this really mean? Right? What do we? Let me just show you a picture that's helpful for understanding what this really means here. It's the following picture here. So if I put a dielectric inside a capacitor, what happens is that dielectric becomes polarized. So that green chunk right there, the negatives want to move upwards. Right? The positives are left down at the bottom. So what that does is, by putting a dielectric in between the plates, and essentially it reduces the electric field inside the capacitor. Because now you have some induced surface charge, and that induced surface charge creates an upward electric field, which cancels the electric field in the capacitor that's already downwards here. So what it does, putting a dielectric in your capacitor allows you to beef up your capacitance. Rather than just having air or a vacuum in between, you put some dielectric medium in it, and you get a larger capacitance. You have more ability to store charge. Okay, so that's the important point. And for us, what happens is C is going to equal epsilon A over D. Epsilon is what you're going to try to measure. The epsilon of the paper, or the permittivity of the paper. The lowest value it could possibly be is when there's nothing there. That would be 8.85. Right? So it's, the number that you get is going to have to be larger than 8.85, because 8.85 is the lowest you could possibly get. That's the number you're trying to measure the permittivity of the paper itself. That's one of the main points of this lab. One more point here is what happens when you put a bunch of capacitors together. Okay, series and parallel. Exactly here. So, if I put a bunch of capacitors together, you can see what's going to happen. The battery is going to charge each individual capacitor such that the potential across each individual capacitor is equal. Right? Now, what does that work out to be is when you, now this is in your lab. This is in your lab, but if I combine a bunch of capacitors in parallel, you just add them all together to get the total capacitance. If I take a bunch of capacitors and I put them in series, it turns out you add the reciprocals together like this when they're in series. Okay, that's what happens when you combine capacitors together. And we're going to test that out as well just by taking some of these cylindrical type capacitors that are over on the side. This one right here says 22 mu f, or 22 microfarads. I have another one here that says 47 microfarads. You can see that the 220 microfarad one is actually larger than the 47, which kind of makes sense. It has to store more charge, so there should be more. The conductor should be bigger. The surface area should be larger. So these are kind of ones that are rolled up really tightly. Right? The plates are really rolled on top of each other as the dielectric medium is in between. All right, so all the equipment that you need is over on the side. You can also grab some snap connectors, which will help you build the circuit. The snap connectors just have these little snaps on the end, and a snap them in place, and then you can build things that way. All right, so the exercise you have is just a warm-up exercise, which will be helpful for answering some of the questions in the lab. You can do that during the lab. You don't have to turn in the warm-up exercise. It's just for practice.
Yeah, we just have a lab, right?
We already did that.
We need the 2